Okay, thank you all for joining this webinar on wind loading from Singularity Engineering. My name is Ming Yao, and I'm the founder of Singularity Engineering. Today, I'll be presenting this webinar. It's my first time using the new streaming tool in YouTube, so please forgive me if there are any issues. If there are problems, I'll monitor the chat, so please type something in and let me know if there are any issues. So with that, let's get started. Thanks again for joining me, and let me I think I need to turn off. There we go. Okay. There's some feedback on my side, but I think we're okay now. So today we're going to talk about wind loading. We're going to start with a very simple model. I've worked on wind loading for a number of applications. Many years ago, I worked on some examples of solar panel wind loading because solar panel needs to withstand hurricane or tornadoes. Lately, I've been working more with cell phone antennas. It's kind of tower antennas, and they also need to withstand wind loading. So I put together a very simple model. Here is your standard rectangular antenna, and I'll go through the whole process of wind loading. I have a plan here on what I will talk about, so let me bring that up. Okay, so it's going to be a few quick topics. We're going to start with initial geometry, to set up a pseudo 2D simulation so it runs quickly. We'll monitor forces to look at what happens when you do wind loading. We'll do some mesh changes, adjust the Y plus boundary layer, wake refinement, add some fillet, switch to transient, and look at some other turbulence models. So it's a packed agenda, but so I'll get started. So first thing is this is an antenna. These are often 6 feet tall, so they're fairly large antennas. If we try to test this, you need a very large wind tunnel, and what we found is that wind simulation can produce very accurate results. With simulation, we can model the full 3D model, so we can imagine we put this into a big wind tunnel and put a box of air around it, or we can do a pseudo 2D simulation. So there are many different ways to do this. If we want to do a 3D simulation in SpaceClaim, I do the enclosure option and just pull this out to the right size. So we can, for example, pull this, you know, something like that. This obviously results in a fairly large simulation problem, and I wouldn't be able to solve this live for you today. So let's go back and not do and do this a different way. So we can also sketch out our antenna. So assuming this is the direction of the air, we can draw a box that represents the outline of the antenna, and then I can define a rectangle from a center and draw, you know, an area where the wind will be blowing. So let's do that. The larger we make the box, the less effect we have on the walls adjacent to the antenna. Um, and then we can pull this, so I don't need the solid anymore. I can just pull this a little bit. Let's make it 10 millimeters. Okay. So I have a shape that looks like this. Um, you typically for wind loading, we want the wake region is kind of interesting. So you can imagine flow coming in here, and there's not much going on upstream. But as soon as the flow hits our object and starts to flow downstream, there's vortices, there's wake region, and that's usually fairly long. So we probably want to make our wake a little bit further. Um, another meter, let's say. In comparison, our upstream doesn't need to be quite this long, so we can just drag it in to keep the simulation small. So this is what we need to do our analysis. I'm going to save this. And this geometry preparation can be done in almost any tool. I'm doing this in SpaceClaim. Then we can go to AIM. AIM is a really nice tool. It's the ANSYS easy to use multi-physics environment. You can do fluid flow. which is what I'm doing here, but also structural mechanics, thermal, and electromagnetics. The reason I'm using AIM is that it's very easy to use. So if you haven't done wind loading simulations before, this is a great way to get going. The other reason that it's very cheap. So if you have done wind loading or if you have contracted out, getting a year's lease of AIM license is going to be a lot cheaper than what you need to do to outsource it or have someone else do this for you. And you can see that it's going to be pretty easy. So we're going to connect to an active CAD geometry. It knows that I have space claim open. I'm not going to define mesh manually right now, although this is necessary, or I guess it would be nice to have to do so. And I'll just go ahead and do the standard setup. So is it going to have heat transfer? I'm going to turn off everything and just do a steady state flow simulation for now. The fluid region will be air. If we get into high Mach numbers, we can use compressible flow. If we decide to look at particles and droplets, we can turn on particle. But for now, we're going to keep everything really simple. And it sets up this work frame for us. So take a look at the source. It recognizes I have an active CAD model open in SpaceClaim. If you have CAD interfaces with SolidWorks, NX, um, Siemens NX, or Creo, it'll recognize all of those as well. Then we can set up the flow. So um, all of the red exclamation marks are things that you need to fix, and if you right click, it'll ask you to fix it here. So let's define this region as our computation domain. Then we can specify inlet. This will be this surface here will be the inlet, and the velocity is going to be 100 miles per hour. Mile per hour. Okay. In AIM, we can put expressions, so we can uh, write the speed as a function of location and distance. So if you have like a city level simulation, you can write an equation that describes the velocity change as it goes up higher in altitude. Uh, if I have an inlet, we need an outlet. So this will be a simple zero pressure outlet. And the two slices here, this will be symmetry planes. And AIM should pick up the rest automatically. So then we can go ahead and run it. So I'm going to be making some mistakes on purpose. So don't be alarmed if things don't quite work out well. We're relying on automatic meshing because obviously if you follow the workflow, this is the process that you would go about getting a solution. So we have a solution monitor here. If you're familiar with CFD, CFD is highly nonlinear, so we monitor the convergence. We want the convergence to drop below 10 to the minus 5, and you can see we have a lot of oscillatory behavior. It's not really getting to a good convergence. AIM has a really good solver, so if you're doing a steady state simulation, we do expect it to typically converge between 100 and 200 iterations. Usually when it doesn't converge, we want to take a look at the results to see where it got to. There's vectors. We don't want to look at vectors. So I think one of the things we would probably want to take a look at is the contour surface at the top. And let's take a look at, for example, velocity magnitudes. Knowing this is not the right answer, right? It's a partially updated answer, right? A few things we notice, right? Big blotchiness in the coloring. And this is an indication that our mesh is far too coarse, right? So with computational fluid dynamics, it's very important to have boundary layer resolution, and the mesh here doesn't look all that great. So what this means is that we should then define the mesh manually. So meshing is a big part of computational fluid dynamics. Getting the right mesh would inevitably help you to get better results. One of the nice parts about meshing in AIM is that you can, or doing a 2D slice here, is that instead of a tetrahedral mesh, we can do automatic, and that's going to switch this to a hexahedral mesh. Or if you know that you can do it, let's go ahead and generate this mesh. So a good tip here for wind loading is that when you're doing wind loading, it's almost always beneficial to have a this manually defined mesh option set, right? Um, so this is the mesh. You can see that ANSYS automatically tries to resolve the boundary layer on both the side walls as well as the antenna itself. So the mesh here is 2 cores, right? We want far more resolution than what's offered here, so we can go in and adjust these values. So right now our maximum phase size is 0.4. Let's do 0.1. Because this model is using curvature refinement, that's what's causing these mesh to be larger. And usually there's a little box that shows how big the mesh is. I think my my global coordinate system may be a little bit far. Okay. So you can see now we got a bit better resolution of the mesh. So let's go ahead and try to run this now. Another tip of when you start wind loading is I highly recommend you start with something like a slice here, because you can see how fast the simulation goes. You can really try a lot of different ideas and options to try to get to fine tune your settings before you tackle the full model. Sometimes people try to tackle the full model too quickly, and that causes issues. So you can see that with this mesh we have 173 iterations, and it converged down to 10 to the minus 5. So it did reach a converged state, and we'll update our results and take a look at the contours now. Okay. So for steady state model, this looks pretty good. You note that the wake ended up hitting the outlet. This is typically not recommended. We want to extend our wake region further so that our outlet is not affected. So I can just go in here and say, okay, in that case, let's pull this out by another maybe 2 meters. We can just synchronize, and ANSYS will automatically bring that new model in and maintain all of our changes. So this makes setting things up more more easier as well. Let's do a generate mesh. And this time, let's set up the force monitor too. It's we're doing wind loading, so when we want to know how much force is being applied on these surfaces, um, we can add a chart. We want to monitor. Let's see, add. We want to create a value, and we want to create that value on this area. Oh, no, we want to just replace that. So on these 4 faces, we want to look at the sum of the force in the x direction. Okay. So now it's going to run the simulation, and while it's running the simulation, we can keep an eye on what the force looks like in chart number 2. So you can see initially there's quite a bit of nonlinearity, then the force kind of stabilizes. We have about 10 newtons of force on this part. And that's what we want to see. We want to be able to predict what the forces are. Looking at the contours again, you can see it's starting to spread out. I think ideally I'd want this even further from downstream, so as to not influence the pressure distribution upstream. We can also look at the pressure. right? And that's you see the high pressure area over here. One of the key things we want to that's needed when we do these type of simulations is to use the right turbulence model. We're using ANSYS defaults to the shear stress transport, which is a very nice turbulence model developed right here at ANSYS. But for that turbulence model to be accurate, we need to have y plus of around 1. Y plus is a calculation of the velocity as well as how far you are away from the wall. So let me try that again. And we can just plot the y plus here. So y plus is a measure of how fast the first layer of elements flow speed is, and you can see that we're way over what we hoped it to be. So we can go back to our meshing and go to mesh controls. There's a boundary layer control that's set automatically. This is actually set on all 6 faces, so I'm going to leave this as leave this control on the 2 outer faces because I don't really care about the flow very much here. So I should change it to 2 faces. And on the inside, I'll add another boundary layer control. Here, instead of using smooth transition, we're going to manually define the first layer thickness. And let's get 20 layers going here. Let's say a millimeter. Take a look at what the mesh looks like. So since the y plus is directly proportional to how your first layer is, being able to define a 1 millimeter mesh here allows us to have an idea of what our y plus result is. We can control it better. So if it's 10 now, we'll just make it a tenth of a millimeter. Okay, converge after 136 seconds, and our force went up maybe 10%, right? It went from 10 something to 11 something. Right, so by refining the boundary layer, we're getting more accurate results. So this is our pressure distribution and y plus. Still quite large over here. I should probably reduce this a lot more. So let's go find our mesh control, the second boundary layers, and we'll toss another. And we probably should add another, let's say 5 layers. The other thing is that when we generate these mesh, we want the transition to be smooth. So we don't want there to be a huge difference between the element before and after our, like, this is a big element right next to a very small element. So we want to transition that, craft this mesh much more carefully. Okay. And now let's run this again. So again, it's really nice to work with 2D models or pseudo 2D models like this. You can crank through a lot of simulations really quickly, and it helps you to really understand your environment and what kind of settings you want to get accurate results. As you can see, our Y plus dropped from about 50 to 7, and it's 0.5. So most of this is probably below or in the range of 1. I could make it even smaller to really hit that one, but let's see if it made much of a difference on our calculated value. So it's about 11.7 now. It was 11.3 before, so we're talking about 0.5% of or 5% now of force change, which is pretty good. So I've shown you how to set up a monitor, hex mesh, Y plus, and boundary layers. The next thing that we want is usually to try to refine the wake. If we look at, we know in fluid dynamics, velocity plays a big role in establishing the flow pattern, and you can see there's some discontinuities as my mesh size gets bigger in the wake. And this is, if I turn on the mesh here, we want, we can capture gradients using these mesh elements, and they don't really do a great job of capturing the gradients over here. So we can adjust this model and set up some wake, um, set up a region where we want to refine the mesh even more. Usually we want to do a few body length downstream. So again, we go back to our CAD model, and I'm going to do a we'll sketch on this, and I'll just draw a region. Snap to grid. The grids are very small. Let's do this. Maybe from somewhere over here all the way down here. So I'm drawing a box, and within this area we'll have a very much refined mesh, and that lets us capture the wake better, and this will be very useful for later procedures too. So and that's just on one side, so we want to project this onto this side as well to cut it. Oh, okay. So now we have a model with two sides. We don't need this little surface here, so let's get rid of it. So going back to the model here, let's synchronize the model again. Okay. And here on the mesh now, we can assign some mesh sizing. So size control, face sizing. Remember previously we had 1 millimeter, or we have the mesh size set on the entire model. Now we're going to have a smaller one. That kind of gives you an idea of how big the elements are right now. Let's see what. I think that's probably what we had before. So let's make it a tenth of that. Oh, that looks a little too small. We're always balancing how long it's going to take to run the simulation versus how much accuracy we're going to get out of it. So that looks like a good trade-off between accuracy and speed. And obviously, to do this formally, you want to refine the mesh and see if if the values change for the variables you care about. Symmetry, because we added two surfaces, and this is saying, hey, what about these two surfaces? Um, we got new surfaces that maybe shouldn't be there, so let's swap it out, and now it's good. Contour plot, my velocity magnitude, it says, hey, this phase changed as well, but now we want to plot it on both. So remember last time we ran it, we had about a drag of 11.7 newtons. All right, so 11.2. So by refining the mesh, we're getting results because we're resolving our flow region more accurately, and you can see that it converges in about 100 iterations. Let me quickly check the YouTube chat to see if anyone have questions. Oh, someone asked, does it work with CATIA? It certainly does work with the CATIA. We don't have I think there is an interface with CATIA. CATIA is a bit troublesome these days because they, let me pause it so I don't hear myself. CATIA does not provide external connections with other simulation tools these days, so it's a little bit cumbersome to work with CATIA. I should have saved this, but it looks like maybe AIM, maybe I'm trying maybe the streaming and the solving and the display of it is taxing it a little too much. So that's okay. We will quickly shut this down and do a quick reboot. Maybe this will come back up. Yeah, I think maybe I moved too fast in trying to plot the results or something. Okay. We're gonna move on anyways, but with a quick reboot and restart of this should bring us right to where we want to be. So the next thing I wanted to show you, so to finish the question about CATIA, we can import geometry from CATIA, but this direct link where you can quickly modify the geometry and then uh, run the simulation and then iterate back and forth, that's a little bit more difficult with CATIA. Mostly other tools we have direct interfaces with, and obviously ANSYS is always working to try to improve that connection, but we have to license the connection from, our partners, and some companies are hesitant to establish that link. So it's okay. So I think the next thing, once we refine the way, because we want to make some additional changes to the geometry. So a really nice part about this is that I can um, select these edges, right? So, having a perfectly rectangular and sharp antenna or shape probably isn't a great idea. It's likely to be um, all kinds of issues with sharp things, right? You have fatigue issues structurally, and on CFD side, having sharp corners tend to increase your wind resistance. So what happens if we soften those corners and put some fillets in? And these fillets can be parameterized, so I can easily adjust them to and have ANSYS automatically run through a series of simulations. So let's import our new model in. I think I definitely want to define mesh manually. Okay, so a quick recap of all the things we did. We adjusted the global size setting. Wow, 1 meter, that's really huge. So let's do 110 centimeters. On the mesh control size, elements, we want this to be automatic, or actually hexahedron. And boundary layer, we want two. So one, the easy one is over here. So let's, and then the other one we want in the actual antenna area itself. There's actually a display setting. Um, there's an option to standard display versus enhanced display or translucent. Enhanced display is a little bit more taxing, so I'm suspecting that maybe my GPU couldn't handle having all of these display options going at the same time. So uh, maximum layer, so we want to set first layer thickness. I think we wanted 0.1 millimeter, and maybe let's have 35 layers of boundaries. Let's see how this looks. Okay. Um, and we wanted to add sizing, face sizing on these two faces. So ANSYS has this little selection plane. If you're familiar with Workbench, it's the same thing. It lets me see select things below it that I don't readily see. Um, how's that? Seems a little small. Sure, let's do this. It's also good policy to keep track of how many elements you have in the mesh. For example, this I may have overdid this a little bit. It's taking some time meshing. Let's stop the mesh. Okay, quick check on, see if anyone has chat. Okay. Yeah, if anyone have other questions, feel free to start to write them down in the chat window. So what did it say? Oh, wow. That's so it shows you what happens when it try to mesh it. Something very strange happened. So so go back to our mesh controls and see what the issue is. So we have a few mesh controls: boundary layer, element shape. Oh, it seems to have never implemented the sizing thing. Okay, so it has a size control, boundary layer. Let's see if it works better this way. Hmm. Oh, it doesn't like this these mesh controls for some reason. What if I just do one of them? Maybe I have to add these ones too. Let's see. Let's try, and then I'll move on from that, from this part. Okay. So something is wrong with this mesh setting. Um, let's just reduce the entire mesh. see if that can help us resolve some of this stuff. I wonder if something's wrong with this geometry. Looks fine. Okay, so we'll go with this for now. Some strange stuff happening here. One volume, boundary layer, boundary layer. Okay. Okay, so let's move ahead here. We want to ensure that this whole body is picked for a fluid domain, and set up the boundary conditions again. Okay, do 100 miles per hour, and we have an outlet here. Of 0 gauge pressure. Select the surfaces for symmetry, and I think the last thing we want to do is add a monitor, chart monitor. So we want to create a calculated value of these faces, 8 faces, and we want to do a sum of force in the x direction. Okay, so we're back to where we were, and the next on our list is we have added the fillets. So let's go ahead and evaluate this. I think the last time we ran it, it was 11.2 newtons. So let's see if adding fillet made this different. Okay, so now we have a very low value. Was the flow rate correct? Yep. And we can look at the velocities. Oh, oops. Let me select these surfaces and add a contour of velocity magnitude. Okay, so you can see that instead of having, we still have stagnation, but then the flow can accelerate around here. We have some high pressure, high velocity area, which means it's low pressure over here. So there's a suction going on, and that pulls this a little bit forward. We can also take a look at the pressure. Okay. So by adding fillets, we significantly reduced the wind loading on the structure quite dramatically. Actually, looks like it became a third of what it was before. So the next step we want to do is transient. These simulations are tricky because the flow isn't always steady. If we look at the velocity distribution, you can see that right now it's predicting this wake that's kind of uniform going back behind our antenna. In reality, it would only ever be like this if the flow is completely balanced on both sides. If there's any sort of instability where flow would slightly be faster on one side or the other, or there's a gust, then you would see this wake start to wiggle back and forth. So for many problems like this, it's actually important to try to run a transient simulation and monitor this analysis. So we can do that in AIM. I'm going to run it for 1 second, and we have to specify an initial condition. So initial 0 pressure, and we'll have 0 velocity in all directions. So let's get going. Transient simulation takes much longer. The nice thing about AIM is that, as you saw, we don't have to specify the time step. AIM uses a different time stepping calculation, so it does a first order and second order time stepping and see what the difference is, and that allows it to adjust the time step to try to capture things that's happening in the flow automatically. So this makes it much simpler to run transient simulations. And you can see it's going here, and it's calculating our um, our drag on the cylinder. So this is one of those things where historically, whenever we did transient simulation, it was very there's a lot of trial and error. You try to calculate what the possible frequency of vortex shedding is. You do an estimate, set time steps, run the simulation. Sometimes you need very small time steps. Sometimes you can try to take larger time steps. So there's a lot of uncertainty in determining that. With AIM, we can just set it up and let it run, and it automatically tries to capture the right flow features. And at some point down the road, it should start to show some unsteadiness. Initially, we assume the flow is stationary, so then suddenly we have a gust coming in, and the flow will develop. We'll see kind of the wake form, and then small instabilities would cause the wake to kind of wiggle back and forth, and that's when we should see some interesting things happening. So I think there's small oscillations happening now, and you would expect these oscillations to start to build, right? So back here, we have a force of about 3, which is what our steady state simulation showed. But you can see that as time goes on and the flow starts to, the unsteadiness and the vortex shedding starts to develop. We're going from 4, 3.8, and now it's up to 5. So I'll let this run for a bit. This is all running on my laptop. It's a Dell workstation, so it's new, but it's not certainly the best computers available. And AIM is highly scalable, so if you have a large workstation or a access to a cluster, you can run this on a lot of cores, and then it's very feasible to do full 3D transient simulation like you see here, right? So this is what we're seeing, the unsteadiness causing larger and larger fluctuations. The fluctuations will increase, and at some point it will kind of come to a steady state, and that's the force that we're actually interested in. We don't care about the situation where the flow is perfectly balanced, right? In real life, when a wind gust hits an antenna like this, we are more interested in the maximum force that gets exerted, and that's going to be when this type of unsteadiness stabilizes, and it'll tell us what the maximum force. And the frequency is also useful. We want to see what the frequencies are. You can potentially use that to do um, life analysis. If you have an idea of how often you see different levels of wind, what kind of vortex shedding occurs at those different speeds, you can do probably a random vibrations analysis. And random vibe would help you predict the durability of your support structures over time. So now that we've gone more than 200 points, you can see that we're wiping away some of the initial results, and this gives you a more clear view of how the flow is developing. Initially, it's kind of steady because the flow is developing, and then once it reaches this type of oscillatory behavior, you can see it's starting to flatten out. It increased, and then it kind of stabilizes in this 8.5 to 7 regime. Um, I'll let it run for a little bit longer, so just so we have some nice pictures to look at the end. With ANSYS, we don't save every single time step automatically. There's options to save you know, um, there's like a small, medium, large bucket of how often you want to save. I think the default is medium. So it probably takes your entire duration and maybe saves 200 points or so in between. Years ago, I was at a CFD conference, and one of the speakers said, "Hey, if you have a model like this and your tool can only predict kind of steady state behavior, that's not really useful." And we see that here because in steady state, we predicted a drag of like 3 newtons. But in reality, with transient, it's much higher, right? It's 0.8, but it's still better than our square-shaped antenna, which was at 11. So this is a 20-30% drop from that, but it's certainly not a 3 Newton force like we were hoping with a steady state simulation. So transient simulations are super important um, for wind loading. We want to see what the maximum force is and also the frequency of the vortex shedding. It lets us predict durability. And AIM is really nice in that it allows you to just say how long you want to run, hit go, and it'll automatically figure out the right time steps for you and capture these behaviors very nicely. So it's I have this running all the way to 1 second, so it looks like it'll take a bit longer, but in the interest of time, I'm going to stop this. And we can take a look at the results, specifically our contour of velocity. Okay. So if we play the video, you can see the flows developing this types of vortex shedding. A couple things that this vortex is kind of getting close to the corner. I don't really want that. If we want to model this device as sitting out in the middle of nowhere, our boundaries need to be further so it doesn't influence the flow. Our back could be longer to try to remove any upstream effects. But um, that is that shows you the vortex shedding, and you can see that there's almost nothing. I didn't need to do any calculations to figure out the frequencies to adjust the right time steps so that the flow is stable as well as capturing the frequencies. AIM does all of that, and this is really one of the best things about AIM that was put in. AIM has a lot of advanced technologies. Um, we can go to our calculated value, evaluate it. So this will calculate the force on the on our antenna, and we can plot a graph, right? So you can see ANSYS didn't save a whole lot of data. We got some bumpy, zigzaggy data here. You can export this to a CSV file. I'll just show you when we're solving output controls, right? There's a output frequency, medium, low, high, and then time steps and interval. So you have a lot of controls available. You can also choose what you want to save. In this case, we want to save everything. Um, so lastly, I wanted to switch this back to a steady state because I want to run one more thing and show you. AIM by default switches to some of the uh, most advanced options available, but we have the option of picking different turbulence models. There's even the option of doing boundary layer transition, so laminar to turbulent transition, if you want really high accuracy simulations. We've done this for, and curvature correction for highly swirling flows, such as pipe or flow around a rotating disk. But a lot of times people use the standard K epsilon model. This is one of the first two equation models out there. and it's not the default model, but it's in there for you to correlate to other simulations. But we certainly expect K omega SST to be better in every way. But you can certainly switch to a K epsilon model, solve the simulation, and the result could potentially be quite different than what we saw with our K omega SST model, especially if we're able to capture the kind of flow velocity in the corners and as near boundary surfaces. So typically K epsilon is good for free stream um, mixing of jets, and K omega is good for boundary layer flows near wall, and obviously for uh, this type of wind loading, we really care about what happens near the wall. So usually K omega is better. SST, the K omega SST model is a blending function between K omega and K epsilon. So it's you know better than both of them because it captures everything. Okay, so it looks like K epsilon has trouble converging here. I'm going to stop it because it doesn't capture the boundary layers. And then we can take a look at the results. Okay. That's the K epsilon result, and if we look at the calculated value, right, 2.7, so versus 3. So K epsilon is not recommended, but wanted to show you the option that it is there, and obviously we try to make sure our solvers are accurate, and K omega SST is the default setting, so this is the certainly preferred for all applications in ANSYS AIM. That covers everything I wanted to discuss today. So a couple of key things, if you are not used to doing this type of simulation, is if you want to get started, get AIM. You can download it. You can get a 1 month trial free on the ANSYS website. Let me take a look at. Try to find the website for you. So if you look, oops, discovery. There we go. Right. If you look for ANSYS discovery trial, you can go here and sign up for a trial of ANSYS discovery. A 30-day trial automatically started. If you're at the end of that, you decide to buy the software, let me know. Contact us at Singularity Engineering, singularityeng.com, and we'll make sure we get you access to this. So start with a 2D analysis. This, no matter pretty much no matter what you do, the first model should be a pseudo 2D. I don't care if you're doing like a solar panel or a building or um, an antenna, right? Start with a 2D so you can quickly, in an hour, right, go through 6, 7, 8 different settings, make sure that the results are reasonable, and then go for a large model. Some of the key things we learned today is, the manually control the meshing so you can refine the mesh near the structure. Uh, Try to refine the wake region. I had some issues at the end, but we can sort that out easily if you decide to try to do that. So refine the wake region. Don't rely on the default setting for these type of pseudo 2D models. Even for 3D models, meshing is really important, right? Before we had this mesh versus the having a boundary layer mesh would change your results by 10, 15, 20%. So having a good mesh is important. And finally, doing a transient simulation so you have um, you know, you get the transient behavior for this type of blunt body models is really important because in testing, you're never going to get perfectly symmetric flow in your system. So doing a transient simulation gives an idea of what you would actually see in a wind tunnel versus idealized simulation results. That's it. That's all. Thank you all for your interest. If you like this, please subscribe to our YouTube channel. We have lots of webinars coming up the rest of the year and coming year. If you're interested in talking about simulation of any kind, let us know at singularityeng.com. I'm gonna start shut this down. Let's see if there's any additional questions. I don't see any other questions on the chat, so feel free to email us, visit our website, and subscribe to this YouTube channel. Thank you, and hope you have a great day.